wanted to work through the example of the relativity worksheet. It's a worksheet that involves near light speed travel from Earth to a star by an astronaut, by an astronaut dog. It's a problem that involves length contraction, a feature of relativity, and it's a problem that involves time dilation, another feature of relativity. There's a sketch of the problem here. On the left-hand side is Earth. On the right-hand side is a star. There's 90 light years distance between the Earth and the star. Remember, a light year is the distance traveled by light in 1 year. It's an enormous distance because light travels at 300 million meters every second, and there's roughly 3 times 10 to the 7 seconds in a year. So it's an enormous distance. The astronaut dog, travels from Earth to the star at a speed. We're told that speed is, told it in actually a later part of the problem, but that speed is almost the speed of light, but not quite the speed of light. It's the square root of 81 over 82 times the speed of light, so fractionally less than the speed of light. Few remarks. There are 2 frames of reference relevant to this problem. One frame of reference is the frame of reference of the Earth and the star. In the Earth frame of reference, the Earth and the star are fixed in position. And so that's the Earth frame of reference. The other frame of reference is the rocket, the astronaut, the dog astronaut frame of reference. That's the second frame of reference. So with those 2 frame of references, if you're in the Earth frame of reference, you see the rocket moving with respect to your frame of reference. You're in the rocket frame of reference, you see the Earth and star, the Earth frame of reference, moving with respect to your frame of reference. If you're in the Earth frame of reference, you're going to see the rocket frame of reference move towards the right at a speed that is the square root of 81 over 82 times the speed of light. If you're in the rocket frame of reference, you're going to see the Earth and the star moving towards the left at that same speed, a square root of 81 over 82 times the speed of light. The proper distance between Earth and star is measured in the frame in which the Earth and star are at rest. It's measured in the Earth reference frame. So when we talk about the distance between the Earth and the star, the proper distance is in the Earth reference frame. In the rocket ship reference frame, you'll see a contracted distance. The proper time between the rocket ship leaving Earth and the rocket ship arriving at the star, that proper time, on the other hand, is measured in the rocket ship reference frame, because in the rocket ship reference frame, leaving and arriving, leaving the Earth, arriving at star, are actually at the same location. They're at the location of the rocket ship, the door to the rocket ship. So in the rocket ship reference frame, we see the proper time. In the Earth reference frame, in which the rocket ship is moving and the rocket ship clocks are moving, in the Earth reference frame, we're going to measure the time, dilated time for the trip. In the first question, we're told that it takes light 90 years to get from the star to the Earth, or from the Earth to the star. Can the dog get to the star in less time? Can the dog get to the star in less time from the Earth perspective, Earth reference frame, from the dog perspective, the dog astronaut reference frame? From the Earth reference frame, the answer is no. You can't go faster than the speed of light, so the maximum speed that light can travel that an object can travel from the star to Earth or Earth to star is the speed of light. If that takes 90 years, then from the Earth star perspective, you can't get from the star to the Earth or the Earth to star any faster than that. From Fido's perspective, the answer is yes. You can get from the Earth to the star or vice versa in less time. So from the Fido reference frame perspective, from the dog reference frame perspective, you can, because in that frame of reference, the distance between the Earth and the star is the contracted distance. And that contracted distance could be much less than the proper distance. And so in the dog reference frame, the dog and rocket has to travel less distance. It could cover that less distance in less than 90 years. In the second question, we're asked to look at a sketch of Fido traveling from Earth on the left to the star on the right. We're asked why Fido looks compressed. This is a sketch from the perspective of the Earth reference frame, in which the Earth and the star are at rest. So the Earth and the star look normal because they're at rest, but Fido, who's moving very fast in the rocket, Fido and the rocket are going to be Lorentz contracted. They're going to be relativistically contracted. And so along their direction of motion, they're squeezed or compressed, they're contracted. And that's why we see their strange shape here, their weird shape here. Actually, there's another question comes up later on. It's question number 5, which is sort of the reverse situation. This is a situation in which we're viewing the travel from the rocket ship reference frame or the dog reference frame. Then the dog and the rocket ship look normal. But in this case, Earth over here on the left and the star over here on the right, they're moving fast. They're moving towards the left rather than to the right. They'll be Lorentz contracted from the perspective of Fido's reference frame, the rocket reference frame. And so they'll be weirdly shaped like pancakes as they travel very fast from the right to the left. The next two questions ask us about the time it takes the rocket to travel from Earth to the star. And actually in the first part, 3, is the time for the rocket to travel from Earth to the star in the Earth reference frame. And then in the second part, it's problem 4 here, it asks for the time for the rocket to travel to the star in the rocket reference frame. And we've already said that it's the rocket reference frame that measures the proper time, because the arrival and the departure and arrival at the same locations in that reference frame. It's the Earth reference frame that measures the dilated, this longer time, because the departure and arrival at different locations in the Earth reference frame. So we're going to calculate these two time intervals. Before I do that, I'm going to calculate one more thing. It's the Lorentz factor that corresponds to this velocity v, which was the relative motion of the rocket with respect to the Earth reference frame, or vice versa, the relative motion of the Earth reference frame with respect to the rocket. So to calculate gamma, the Lorentz factor, if you remember, it's 1 over the square root of 1 minus v over c squared. Now, we have been told that v over c is the square root of 81 over 82. So actually, v squared over c squared is simply 81 over 82. If v squared over c squared is 81 over 2, if this quantity here in the Lorentz factor is 81 over 82, well, think of the 1 as an 82 over 82, less than 81 over 82. This quantity inside the square root here is going to be 1 over 82. So we can rewrite this as 1 over 82, and 1 over the square root of 82 is actually just the square root of 82. And the square root of 82, I already figured it out. It was 9.055. And so that's the gamma factor. Now, I did it by just juggling around square roots of 81s and 82s. You could have just calculated what V is as the square root of 81 over 82 as a decimal and plugged that in. That's perfectly fine too. So now we know the Lorentz factor. That's going to help us with these two questions here. The way we're going to solve these two questions here is first we're going to use a law of physics. We're going to use the law of physics to find the time taken in the Earth reference frame for the rocket to make the trip. And that law of physics is just that speed is distance over time. And then we're going to, in the second part of this problem of finding the times, we're going to find the proper time from that dilated time in the Earth reference frame. And we're going to use the Lorentz factor for that. So let's start with the calculation of the time that's seen in the Earth reference frame. That's the dilated time. And our starting point is what I would call a law of physics, is that the speed or velocity here is the distance traveled divided by the time taken. This distance traveled is the proper distance, because distance measured in the frame where Earth and the star are at rest. This time taken is the dilated time. So I put a subscript naught on the distance because it's proper distance. I didn't put a subscript naught on time because dilated time. We know V, we know L naught. All I've got to do is rearrange this for the time that is taken. So it's going to be L naught over V. And then I just got to fill in the fact that 90 light years, I'll call it CY, the light years, divided by, what is the velocity? It's this 81 over 82, square root of 81 over 82 times C. And if I carry out this little calculation here, I've already done it, of course, that came out to be 90.55 years. You'll notice here that the C in the numerator, C in the denominator cancel, and I just get the units of years. And that's the dilated time that the Earthlings see the rocket ship take to get to the star. Now we want the proper time as measured in the rocket ship reference frame. To get the proper time, we're going to use the relationship between the dilated time and the proper time. T naught is the proper time in the rocket ship reference frame here. T is the dilated time in the Earth reference frame here. And here's the Lorentz factor that we said we were going to need. I'm just going to rearrange this because I want the proper time from the dilated time. Now that means I've just got to divide the dilated time by the Lorentz factor. The dilated time was 90.55 years. The Lorentz factor was 9.055, and you can see the answer here. It's going to come out to be 10 years. So the dog rocket ship take 10 years to get to the star, so the dog can make it before he dies. Part 6 of this worksheet says, calculate the distance from Earth to the star in the rocket ship reference frame. We already know the distance from Earth to the star in the Earth reference frame. That was the proper distance, and that distance was 90 light years. We're being asked to calculate the contracted distance, which can be less, in the rocket ship reference frame. For this calculation, we're just going to use the Lorentz contraction formula that L, the contracted distance, is equal to L naught, the proper distance, divided by the Lorentz factor. In this particular case, it's the proper distance we know, it's the Lorentz factor we know, so we can just immediately calculate this contracted distance that's seen by Fido and the rocket ship reference frame. So let's go ahead and do this. I'm going to substitute in 90 light years, c years. I'm going to divide through by the Lorentz factor. That was 9.055. It's just a number, it has no units. And then if I carry out that calculation, I get a distance 9.939 light years. You see here, the units of the distance L are going to be just the units, obviously, of the distance L naught, because the gamma factor is dimensionless. So we start with a proper distance of 90 light years. We end up with a contracted distance, almost 10, a factor of 10 contraction. That's 9.939 light years. That's how Fido can get there in 10 years, because the distance is so contracted and it's going so fast, very close to the speed of light. He can make that in 10 years. This is the time, 9.939 years, that light would take to travel that distance. And Fido's taking a little bit longer because he can't quite go at the speed of light. The next part of the problem, part 7, asks us to check our calculation of this distance, contracted distance that Fido has seen between Earth and the star. Check it is consistent with the time that Fido took to get from the Earth to the star. That was 10 years, and check it with the motion of the Earth and the star with respect to Fido's rocket ship, which was also at a speed of the square root of 81 over 82 times the speed of light. So the check is going to involve, again, applying this, quote, law of physics, that the speed of the Earth and the star with respect to the rocket, the Earth and star reference frame, with respect to the rocket reference frame, is equal to the distance that's traveled by the Earth and the star. That's going to be the contracted distance now, divided by the elapsed time for the trip of of Fido from the Earth to the star, in which Fido starts with in the neighborhood of the Earth and then ends up with the star in its neighborhood. So that's the proper time as seen by Fido. So all we've got to do is fill in these numbers. These are the numbers that we just calculated in the last two parts. The distance is 9.939 light years. The time is 10 years. And we've got 9.939 over 10, which is going to be 0.939 times c, the speed of light. The years cancel out here in the numerator and denominator. They leave just behind the speed of light. And actually, if you check it, 0.939 is the square root of 81 over 82. So this is consistent. The contracted length, the proper time, and the speed of Fido, the relative speed of the two reference frames, is completely consistent. And there's a few more parts down here. Let me just say a few words about them. In question 8, we're asked, how long does Fido have if he's going to live for 11 years to visit the planets that orbit the star? Well, assuming he visits the planets at a relatively low speed compared to the speed of light, he's used up 10 years of his life for the trip to the star. He's got 1 year of his life left. He's got that 1 year to wander around and visit all the nice planets that are around this star. So there's 1 year left for his work. one year for his vacation. Just to summarize, so for the trip, there are two times. There's the time that Fido, the length of time that Fido experiences the trip to take. Remember, that was 10 years. And then there was the length of time that the Earthlings observed the trip to take. And that was much longer. That was 90.55 years. So the shorter time there is the proper time. That's the time that Fido sees himself and the rocket ship take. So he ages by 10 years during that time. So he physically ages by that amount. From the Earth, we see that trip as taking much longer. And so that's a dilated time that we see from the Earth when we're looking at the time between two events, the departure from Earth and the arrival at the star, that take place at different locations. So there's a key difference between Fido's view of the trip and the Earth view of the trip. Fido's view of the trip is that in terms of location, he starts the trip where he ends the trip. It's just that the Earth moved over to the right and was over to the left, and the star moved over to the left. And his trip was simply from one time to a later time, to 10 years later in time. In his reference frame, he didn't move. On the other hand, from the Earth perspective, Fido's trip is a movement in space of a very large distance. So he's gone from the Earth and traveled to the star. That's a very large change in his location. And in the Earth reference frame, we've measured more than 90 years, 90 and a half years for that trip. And that's the strange thing about relativity. The interval of times between events like leaving Earth, arriving on the star, the distance between locations, the Earth and the star, it depends on your reference frame. That's completely unlike everyday common sense of classical space-time, in which the duration events, the time between two events, is agreed on by everybody. The length of an object, the distance between two locations, Lexington and Cincinnati, is agreed on by everybody. In relativity, that's not true.